Assalamu alaikum. Today I will presenting our work entitled Sustainable Magnetic Biochar Alginate Beads for Adsorption and Photocatalytic Degradation of Methylene Blue in Textile Wastewater. This research was conducted by Hala, Naseer, Abdelkareem, Ibrahim, Abdulwahhab, Mohammed Ali, Abdulrehman, and Ahmed Al-Kamal. Textile wastewater represent a serious environmental concern due to the presence of toxic synthetic dyes. Among these dyes, methylene blue is widely used, chemically stable, and resistant to conventional treatments method. Moreover, traditional wastewater treatment techniques often show low removal efficiency and generate secondary pollution. Therefore, there is a strong need for sustainable, efficient, and recoverable materials for dye removal. The main objective of this work is to study and the synthesis of magnetic biochar alginate beads, abbreviated as MPABS. These beads combine dual functionality, namely adsorption and photocatalytic degradation. Additionally, the magnetic properties allow easy separation and recovery after treatment. An innovation aspect of this work is the integration of an artificial neural network (ANN) model to predict system performance. The raw materials used in this study include biochar as a carbonaceous adsorbent, sodium alginate as a biopolymer matrix, and iron salts for magnetic modification. These materials were selected due to their low cost, environmental compatibility, and suitability for wastewater treatment application. First, biochar was repaired and subsequently modified through magnetic imbrication using iron-based compound. This step introduced magnetic properties, enabling efficient recovery of the adsorbent using an external magnetic field, while also enhancing surface reactivity. The magnetic biochar was then incorporated into a sodium alginate solution. Beads were formed through ionic cross-linking in a calcium chloride solution, resulting in stable and mechanically robust magnetic biochar alginate beads, which called magnetic biochar alginate beads. For the characterization of these beads, several tests were done. SEM tests were used for study the morphology and pore structure. FTIR tests used for functional group identification. PET tests used for surface area and porosity calculation. And VSM tests used for magnetic properties evaluation. This figure represents SEM micrograph of raw biochar, magnetic biochar, and magnetic biochar alginate beads. An observed surface roughness and porosity increase after modification, indicating successful incorporation of magnetic particles and alginate within the biochar structure. TIR analysis was conducted to identify functional groups before and after modification. The spectra confirmed the presence of oxygen-containing groups, iron-oxygen bonds, and alginate associated functional group. That's verifying successful synthesis of the composite material. The adsorption performance of magnetic biochar alginate beads was evaluated using methylene blue as a model dye. The results demonstrate high adsorption efficiency attributed to synergistic interaction between biochar surface size and alginate functional group, and also show that the removal process was a pH dependent and give us adsorption efficiency up to 91.2% with a maximum capacity of 72.6 milligram per gram that follow pseudo second order kinetics with R square equal to 0.996. Photocatalytic degradation was done under visible light activation. Synergistic adsorption oxidation process and give us a degradation efficiency up to 94.5% with an apparent rate constant of 0.016 per minute. This figure illustrates the UV visible absorbance spectra of methylene blue during visible light irradiation. A gradual decrease in the absorbance intensity indicates effective photocatalytic degradation of the dye in the presence of magnetic biochar alginate beads. Operational parameter was systematically investigated. The optimal dosage was found to be approximately 1 to 1.5 gram per liter. Increasing light intensity enhanced degradation efficiency, while temperature show a moderate effect. Importantly, real textile wastewater exhibits competitive adsorption behavior. Reusability tests revealed that magnetic biochar alginate beads maintain high removal efficiency over multiple cycles. This confirms excellent structural stability and highlights the economic and environmental advantage of these materials. An artificial neural network model was developed to predict dye removal efficiency under varying operational conditions. The NNA demonstrates strong predictive accuracy, indicating its potential as a powerful optimization tool for wastewater treatment systems. The proposed material offers a sustainable solution for textile wastewater treatment. It combines eco-friendly raw material, efficient pollutant removal, easy recovery, and AI-driven optimization that make it attractive for real-world application. In conclusion, magnetic biochar alginate beads exhibit outstanding performance for methylene blue removal. The integration of adsorption and photocatalysis along with high reusability and ANN optimization highlights the strong potential of the system as a sustainable wastewater treatment technology. Acknowledgement. The authors gratefully acknowledge the support of the University of Baghdad and Al-Mustansiriya University for helping accomplish this work. Thank you for your attention.